We are going to start with a schematic diagram of chemostat. The chemostat is an open reactor, perfectly mixed reactor. Input flow rate is equivalent to output flow rate. The concentration inside of the reactor are equivalent to the outlet concentration. Everything is constant over time. The following graphical representation illustrates that a chemostat operates in batch mode before switching to chemostat mode, to steady state mode. Substrate concentration decrease and biomass increase during the batch. This provides biomass in the reactor to start the chemostat. Biomass concentration and substrate concentration are constant over time during the chemostat. Let's see now the biomass material balance. In the equation, the accumulation term is equal to 0 because X and V are constant. There is no entrance of biomass because the chemostat has been inoculated by the batch. In this equation, there is an output of biomass and product term of biomass. We replace R triple prime X by mu X. If we isolate Q over V, we will make appear the dilution rate because Q over V is the dilution rate. By simplifying the biomass concentration in this equation, we will demonstrate that mu is equal to D, the dilution rate. In a chemostat, the growth rate is controlled by the dilution rate. This is one of the major results of the chemostat. Let's see now the substrate material balance. The accumulation dAsV over dt is equal to the entrance flow of substrate minus the output flow of substrate minus the consumption term of substrate. All is equal to 0 because d, S and V are constant. The derivative is constant. We can replace R triple prime S by R triple prime X over YXS, and we can replace R triple prime X by mu times X. We make appear in this equation Q over V to make appear D because Q over V is equal to D, and we can simplify by mu because D is equal to mu. This gives us the expression for X in function of S. This is a major result of the chemostat. This expression is a major result of the chemostat. We have just demonstrated two equations of the chemostat. And now we are going to add monomodel to these two equations. With this equation, we will be able to continue establishing new general equation for the chemostat. We will call this equation 1, 2, and 3. With 1 and 3, we replace mu by d in monomodel. Next, we isolate S. For that, we develop the expression. Then we factorize S. And finally, we obtain the expression of S in function of D. By transforming this expression, dividing the numerator and the denominator by d, we can show that when d increases, the denominator decreases, so S increases. When dilution rate increases, the substrate doesn't have time to be consumed, so the substrate increases also. If we replace the expression of S in function of D in the equation 2, we will obtain the expression of X in function of D. So we have obtained S and X in function of D, the dilution rate. We will represent this expression graphically. We will represent X and S as a function of D. When D is small, X tends toward the value X max, while when D tends towards the value of D asterisk, X tends to 0. It is the washing out phenomenon. The trend of S as a function of D is inverse when there is no more biomass. S is equal to S0. When D is equal to D asterisk, S is equal to S0, there is no reaction because of cells wash out. Cells are washed out because they don't have time to grow at the rate of the flow circulating through the reactor. To calculate D asterisk, we replace S by S0 in Modo model. If S0 is very high compared to Ks, then D asterisk is equal to mu max. Let's see now biomass productivity as a function of D. It is the expression of R triple prime X in function of D. R triple prime X is equal to mu times X. Mu is equal to D. And after, in this expression, we can replace X by its expression in function of D. We have demonstrated this expression previously. So we have here the expression of R triple prime X in function of D. We are now using the graphical representation of X and S as a function of D, as we saw previously, and we represent the biomass productivity in function of D. The shape of productivity curve shows a maximum and a minimum, the minimum when the washing out phenomenon occurs. We have a maximum productivity when the derivative of the function is equal to 0, derivative of R to per prime X on dd is equal to 0. We call dm the dilution rate at which productivity is maximum. The expression of dm is as follows, and we don't demonstrate this expression. If S0 is very high compared to Ks, dm is approximately equal to mu max. With d equal to dm, we have x equal to xm and s is equal to sm. We can see that dm and d asterisk are approximately equal to mu max. Thus, depending on the dilution rate, there is either maximum biomass productivity or biomass washing out. This makes chemostat control tricky.